Hi class, as we get started with our first week, I'd like to review a little bit from last semester with object-oriented programming concepts. You've seen quite a bit of information. In this chapter, we'll be talking about abstraction and interfaces. I wanted to, like I say, review a little bit and add in the abstraction component, talking about all of these advanced object-oriented programming concepts. So here I have a transformer because to me, he just exemplifies so many aspects of object-oriented programming with encapsulation and polymorphism and all of the wonderful things that transformers do. So when we're talking about advanced object-oriented programming concepts, we are talking about abstraction, encapsulation, inheritance, and polymorphism. So let's see how our transformer can help us think about those. We know that there are many types of transformers. There are like Autobots, Decepticons, there's other Cybertronians, there could be other types also. And then there can be different characteristics within each of the types. So Autobots, we can have primes. Primes are the semi-type things and heavy duty. And when we're talking about other Cybertronians, we could get really specific, like we have Dinobots and other smaller, lesser beings. If we look at this transformer structure like class structure, we see that we could implement all of the base transformer characteristics, like the transformer's name and other things about the transformer, maybe where they're from, their title, things like that, in the transformer class. We could also include some base behaviors. And then we would want to be able to expand that base to different subclasses to account for all of our different types of transformers. So my Autobot class could inherit from my transformer class. Now I'd like to go down a level, and in order for my prime class to inherit from my Autobot, I need that to be kind of a one-to-one relationship. So I can make my transformer class an abstract class. And an abstract class is one that supplies basic information, but does not supply enough information to actually create an instance of it. So there is no way we could ever have a transformer out there anywhere in the universe that wasn't one of our types of transformers. Okay. He's abstract. Can't just be just. So what about transformers? What kind of characteristics or actions do they have? Well, usually they could walk or drive. They always can transform, right? They can attack, defend, they might roll. So we could have different implementations for all of those different kinds of behaviors for our different types of transform. We might have a different implementation. We might just use the base transformer implementation. It depends on our transformer. If we think about Bumblebee and all of our transformers, they each have a name, they have a function, and a title. This is really behind the scenes type information. We could also keep track of some other characteristics like the number of weapons they contain, when they're fully weaponized. What type of weapons do they have? Maybe a weakness. Maybe we would like to keep track of a state variable like, are they currently transformed or not? So what state they're in. Now, all of these would be private to our base class. Data field. Now, what am I talking about with abstraction? Well, first of all, these pictures are abstract, right? They're abstract. Abstract means I can't quite see the details. I can't quite bring things into focus. When we're working with class abstraction, we are going to make some of our potential abstract class features available. So in our case, our transformer class is going to be marked abstract. We can't make a transformer. We can just use a transformer as a template to make other types of transformers. So we're going to make those features available. We're going to hide the complexity of being a transformer, whatever we can hide within our transformer class. And we'll assume that a transformer can use its transform method to turn into its alternate shape, and the mechanics of that transformation are hidden or abstract. We'd like those too. Okay, so here's some code that implements abstraction. This keyword right here, abstract, is all it takes. So I take this class that I've already created, my transformer class. I have some class variables. I have accessor and mutator methods that I'm not illustrated here on this PowerPoint. I have my constructor to build a basic transformer. I'm not showing the code. And then within my transformer class, I am overriding the system to string to return some string information about my transformer. I'm also implementing a method called attack. And in my attack method, I'm going to expect some sort of integer. My attack method is going to have some code here in my base class. This would be the default attack code, like start shooting, I don't know, whatever we want it to be. Then I also have another method here that I have used that same abstract keyword on, and this method is my transform method. So as you can tell, in our transformer class, we are supplying a base action for our attack, but we are not supplying a base action for our transform. By using the abstract keyword, we're going to require all of our child or inheriting classes to implement transform method. So an abstract class cannot be instantiated on its own. It is a high-level template of the class. To override something is polymorphic. We'll talk a little bit more about that here in a minute. Any non-final Java methods can be overridden, so our attack method can be overridden by subclasses that inherit from our transformer class. And abstract methods must be implemented by our derived or child. Okay, what's encapsulation? I like these pictures. The middle picture here shows a little piece of earth that's kind of encapsulated in this award trophy. I like how you can tell and encapsulated. You can see it, but you can't get to it. Right? Here is another illustration. Here I have some of that laminating, clear, sticky stuff that I'm going to stick over this beautiful form so that I can laminate it. It'll be encapsulated then inside that laminating paper. And then here's a phone. This phone has a really good example of encapsulation and abstraction because all of the components, the hardware components of the phone, are encapsulated or contained within the front and the back, right? And so the front of the phone gives me an abstraction layer that I can use to interface with all of this encapsulated hardware, right? Make things happen and make my phone do what I want it to do. So that's encapsulation. All right, so how does encapsulation have to do with our transformer class? Well, whenever we're working with any class logic in Java, our class is basically comprising a black box. In this example, it's a blue circle, but you could think about it as a black box. And our class contains our private class data fields, and then it might contain public getters and setters or accessors and mutators to allow external access of our private data. Our private data has no external access, no exposure. Now, besides having our data, we also contain the behaviors within our class. So our behaviors, again, are encapsulated within our class, and we can make those behaviors public, allowing them to be externally accessed, actions that can be performed within our class, or we can make them private and make them actions that are hidden from other classes. They're all encapsulated. Some are exposed, some are not. So encapsulation is how we package data, attributes, and behaviors into a single unit, and it lets us hide the implementation details. We don't need to know how to put our phone together in order to use it. So in our transformer example, each transformer is going to have many states and attributes, color, type of weapon, type of movement, and each transformer has behaviors such as transform, roll, and attack. And all of the details of how to implement the attributes and behaviors and how they interact are hidden or encapsulated within the class. All right, what's inheritance? Well, I like this type of inheritance up here. Yeah, no, that's not it. Inheritance is more like over here where we're talking about Marge. Let's see, Marge has developed some characteristics. Right? She has really tall blue hair. She kind of is hunched over a little bit. You know, she has these bulgy eyes. These are characteristics of Marge. Now, Marge probably inherited some of these characteristics from her father, Mr. Bouvier, and her mother, whose name is Jackie. And Marge also has two sisters, Patty and Selma, and they could have inherited some characteristics too. So we might be able to compare characteristics amongst Patty, Selma, and Marge to determine which characteristics were inherited and which characteristics are unique to Marge. They all have unusual hair color. Is this inherited? Well, it could be, but we really don't know for sure. They all have a forward sloping posture. Well, that's probably inherited. Marge and Jackie have similar hairstyles. That's probably not inherited. That's just a choice. Now, this family tree over here might give us a better view here, or we can see a little bit more publicly about what's going on inheritance-wise. We have our grandparents that were a ginger and a blonde, and their children both came out beautiful redheads, and they mated with others, and the redhead and redhead produced redheads. So we see a lot of inheritance of characteristics happening there. Then our redhead combined with somebody that's of a darker complexion created a darker child, so it's not as obvious what characteristics were inherited. Well, whenever we're doing our encapsulation and all of our black boxing that we want to do with classes, inheritance is something that can be apparent, it can be hidden. But, oh wait, I gotta tell you. Here's one, the Simpsons children. All three have spiky yellow hair. Where is this inherited from? Not Marge, not Homer, but look at Grandpa. He has spiky hair. So that must be where that came from. So our child class did not inherit that characteristics from the parent, but maybe from the base class, the parent abstract parent class. So with our transformer class characteristics, let's think about all of that. Our transformer class is our parent class, our superclass, our base class, many names for it. Not my fault, there's lots of names for it, but yes, I will refer to it by many names. Now, our first level of inheriting classes then are derived from the parent class. They can be considered a child class, a subclass, again, lots of different names. And we can continue to inherit again. When we inherit, we always inherit all of the characteristics and behaviors from our base class that are accessible to us. So anything that's public, we are going to inherit. So here is an example of inheritance. So I got a bug there in my presentation. Ignore this one down here, okay? First of all, I've got my access level, and I hadn't really mentioned that, but remember public, private, protected, all of those access levels are important. And as we use object-oriented programming and inheritance, they become more so. Here I have an Autobot class. This Autobot class inherits from or extends our Transformer class. So you could also call the Autobot an extended class, right? Now my Autobot adds additional data characteristics to the Transformer, and it has a constructor here that's a little bit improved. So my constructor includes parameters for all of the base class parameters, name, number of weapons, and type of weapon. But it also includes parameters for all of the subclass data elements. And then in our constructor code, within our curly braces, we have the super specification that specifies which of those parameters should be passed to our superclass to create the instance of that base class that our class will be built upon. Next, we override the system toString, return some information about an object. Next, we override the attack method. If you remember, our transformer class included an attack method, and for our Autobot, we would like to override that. We're going to return a different value. Then we implement the transform method. And if you remember, the transform method is required because, sorry, I'm getting distracted. Our transform method is required because it was something that was marked as abstract in our base class. Next, we have a isAllTerrain method implemented that returns a Boolean value, and this is a state method. It's going to check the status of our transformer and return information about whether it's an all-terrain type Autobot or not. Okay, so first we had our access level, inherits from by the extends keyword, our constructor, base, class, and this extended class parameters, and separates them out using this super. And superclass methods can be overridden. Abstract methods must be implemented by the driver class. And finally, we had that Boolean. So inheritance allows for reuse of the code. Our transformer class could be extended, create any type of transformer. We might create a new type of transformer, a new child class that has different characteristics. Derived classes contain all of the data and methods of the parent class, plus their own data and methods. So let's go on to our next topic, polymorphism. To morph is to take many forms. Which is exactly what a transformer does, right? It morphs. So I wanted to separate the words out. The terms poly means many, so many or much, and then morph is a form of an animal or a plant. So polymorph is to take something and change it into many different forms. And that is what we get to do with object-oriented programming, right? So when we have a transformer, we have, our transform method is an abstract method. But as an Autobot, we can override the attack method, morph it into something else if we don't like it. Our other Cybertronian can implement the transform method to morph it, our Dinobot. So we see how we can take this code and morph it into something overriding method. Polymorphism then allows multiple implementations of the same behavior. So to transform to an Autobot is a different thing than to transform to a Dinobot. So the appropriate implementation should be used based on the situation or your class. For transformers, think about it. Their method might involve rolling or walking, so the appropriate move method should be used. So object-oriented programming concepts overall. A class is a noun, so a transformer is a thing. A child of a transformer is a transformer, right? Still is a transformer. So that's an is-a relationship. Instantiating a class creates an instance. So I could have a variable Bumblebee. It's an instance of an Autobot. Bumblebee is a transformer. Now my data, my class fields and properties, is encapsulated by the class. So a transformer has a name. That's all encapsulated in my class. So that is a has-a relationship. Whenever we're looking at a Autobot being a transformer, that's a type of relationship. Whenever we're looking at data, it is part of the object. So we can have these different types of verbiage used when we're referring to our class and our class relationship. And it's important for us in our mind's eye to be thinking about what those things are. So let's say I am going to implement my class and create an instance of an Autobot. I'm specifying that my data type is Autobot because remember when I create a class in Java, it basically becomes a new data type. So my Autobot is going to be named BB, and I want my BB to be a new implementation of the Autobot class. The Autobot constructor, right, is what I'm going to run. And I'm going to pass in all these different parameters. So its name is going to be Bumblebee. I think it's going to have 4 wheels. Its weapon type is lasers. And then these parameters are parameters that we're using for our, let's see what we got, our Autobot class. So type, num, and type of vehicle. Our type is a Camaro. I guess we have 4 weapons and 4 wheels. And our other type of vehicle is vintage Camaro. So all of these things are specified. That creates an instance called a BB. Now, if we need to get some data out of that instance and put it into a variable that we have, we would use a getter. In our class, but wait, here, this is in our main, right? So this is our tester. Our tester code is the consumer of our class. It's using it. So we created our Bumblebee BB instance, and now we want to get the name from that. We're going to execute then the getName method that's contained within our Autobot class. Well, our getName method within our Autobot class doesn't really know the name. The name is contained within the base class. So our method is going to call the superclass getName. It's going to return the name. That will return and return. Now, is that necessary? No. We can just issue this command, bb.getName, and if that method isn't found in our Autobot class, the Java runtime will go ahead and run that method in our superclass, our parent class, if it's found there. So we can kind of get away from this in between. What about setters? What if I want to change Bumblebee's name to Wasp? I'm going to use a setName method and pass in that value, Wasp. Again, I don't have direct access to that name property. It's private in my parent class, Now I could just make it public, but that would be kind of messy. Some people would do. I could. So I didn't here. Instead, I have a set name in the parent class, and it actually updates our name data value in our parent class. Now, again, is that necessary? No. Our main, when it calls set name, if that method's not found in our Autobot class, it will default to using the method found in our transformer class. So advanced object-oriented programming, the code is simple. I've only shown you like one new keyword, right? The word abstract, I think. But the terms are ours. Abstraction is getting down to the most basic pieces and hiding those details. Encapsulation is hiding those. Oops, I said it wrong, didn't I? Abstraction is getting down to the most basic pieces, but allowing users to access those pieces without knowing the details. Encapsulation is the process of hiding those details within this class. Inheritance allows us to set up those basic details and use them as a template. And polymorphism gives us the ability to use the same method names for multiple characteristics, right? We can have multiple actions from the same piece of code set so that we don't have to reinvent the wheel over and over. Awesome. So you might already be totally clear on all of that. That's great. In our module section, one thing I'd like you to notice is code lens. Show it to you. The code lens has a video, a separate video, but I just wanted to make sure in this video I showed it to you a little bit. You have to click on this link here at the end. In this code lens walkthrough, we're going to create a person class so that you can see some full implementation of object-oriented programming. If you click on the link, it will take you to the code lens system that allows you to get visualization of executing your code. So over here on this side, you can see items that are being created in memory and how they're populated. So I think you'll find it really valuable. Let me know if you have any trouble executing that. It does use a lot of different technology, so it could definitely run into some issues. I hope that really gives you some additional ideas and thoughts on object-oriented programming and gets you all set up to get the calendar stuff, the assignment done for this week. Thank you.